initial conditions were. But in the case of the air bubble rising, it remembers nearly everything about how this thing was started off. And so this is a very different type of beast. And again, it has this relationship to things that we kind of feel about. Is it nature? Is it nurture? And that debate rages even here. So this drop has fallen, and now what does it do? Well, it has to hit something. And so this is an example of something that you may have seen in your in various fountains, where you have water coming down in a nice stream, hits a flat surface, and then creates this water bell. And you can do this in your home. That is, you just take out the aerator from your faucet and let the water fall down on the top of, let's say, the soda bottle, and you'll see a beautiful bell coming out, just like this one here. So this is a similar thing that you've seen. And the question we want to know is, how general is this behavior? And so what I ask is, well, suppose this is water doing this, but suppose I had grains of sand doing this. And so what I have showing here are grains of sand hitting this the surface, and it doesn't look like that at all. That is, each grain of sand comes in and does exactly what you would think. You throw a ball at a wall and it comes right back at you. And so this is what you would expect from individual grains of sand hitting this platform. And now the question is, well, how about if I had taken a jet of granular material? So it was a little bit more like that water case where I have a whole jet of the water coming in. And so that's what this experiment is. So what we have here is we have the target up here. We have a tube pointed at the target. We have sand up to some point here. And we have pressure back here. We suddenly let the pressure go, and we just spit out this whole jet of white sand. And so the white sand starts here. And when I start the movie, you will see this white sand start to move down this tube. Okay, and then what do you think is going to happen? Is it going to ricochet in all directions, or is it going to behave like a drop of water? And so here is the movie, and so watch this white sand coming down. It's target. And so it's behaving like liquid. That is, it's not curling up on itself because there's no surface tension here, but it is going out in all directions in this very, very thin sheet, just like that water belt was doing, the very thin sheet in all directions. And so that's what's happening in this case. And so what changes between that single particle and these many particles, with the individual particles hitting the wall and coming back at you, versus the liquid, or the jet, was that it was the thing that we needed to know was how many particles are in the diameter of that tube. So that's how many particles are in that cross-section. So if we have very small particles, 100 microns, so this is a tenth of a millimeter, we get this very nice thin sheet. If we make it 5 times larger, you begin to get fireworks. When it's 20 times larger, you get this thing really sparkling all over the place. So the granular material is really behaving much more like these individual particles coming back and forth and hitting yourself. Okay, so again, what does this have to do with anything else that I want to tell you about here is that there's, again, a relationship here to a variety of other areas of physics. And so I was able to make a liquid, and I was able to do this without any attraction. The granular material wasn't attracting itself anymore, any more than it was before. And we know granular material is not like a fluid. And it's not due to confinement, as if I was holding this thing in a box and holding all the stuff together, and so that it might look like a liquid for that case. But it's just the kinematics of the situation which is driving this thing to look like it was a liquid. And why is that interesting? Well, it's a classical analog to a very famous experiment that was done a few years ago and still going on at the RHIC collider at Brookhaven and at CERN, at LHC. And this was heavy ion collider physics, and what they did was they took two heavy nuclei, two gold nuclei, and bashed them at each other as hard as they could, and what you get is a quark-gluon plasma. So this is the stuff at the very beginning of our universe. So this is where we all came from. And the big surprise that they reported was that the quark-gluon plasma was a liquid. And the reason that it was a liquid that they could tell was that as this liquid expanded, if there was a thin slot, it expanded in the directions perpendicular to that slot. That was the fastest direction. And so here we have a slot going in this direction, and this is looking at that same experiment from the back. And you see the same kind of behavior. So this is extending in the thin direction rather than in a uniform direction. And so this is the same reason that the quark-gluon plasma is the same reason for its being a liquid as this granular gas is a liquid. And the only thing I would say is these experiments cost a few $1 billion, and I think ours came at $50. And so there's a slight difference, but we're not bragging. Okay, so this is one question about how this liquid is formed, and it raises interesting questions about what it means to be a liquid. There's some very fundamental questions that you get to at these simple tabletop experiments as to basic questions such as this. I mean, so how many collisions do you need to have for it to be a liquid, for example? Okay, so one other thing that drop could have done is if it had fallen on a plate, and then what you would get is a splash, right? So if that drop that had detached comes down and hits a plate hard enough, it's going to splash in all directions. Okay, so what we were interested in is, well, is there anything interesting in the physics of a splash? And so what I want to show you now is a movie of a drop splashing. So this is a drop of alcohol. It's about 3.5 millimeters in diameter, so a pretty small drop. It's dropping from something like this height. So nothing fancy about this. It's going to hit this at a few meters per second. Everything very normal, just ordinary stuff. And the one thing I should point out is that this white thing in here is nothing inside the drop. It's just that this drop is lit from the back, and so you see it's basically imaging the light source, and that's all that white spot is. So let's see how this drop breaks apart. Splashes. So I think that's rather beautiful, and I don't know about you, but I'd like to see it again. So, oops. So let's see it again. So it's coming down. As soon as it hits, it grows that corona, and that corona then breaks apart and splashes in all these different directions. And so the question is, well, what causes a splash? And so, we talked about the liquid, and so it can be, how big is that liquid? If it's a big drop, we know that's going to splash more easily. If it's moving very fast, it's going to splash more easily. So if I take a tiny little drop and lay it very carefully on the table, it will probably not splash. I mean, so we know the size and speed matter. These other things I told you about, like the surface tension, holding this thing in, that's going to matter because how this thing is spreading apart is going to, what's holding it from spreading apart. What its viscosity is going to matter, how easy this fluid flows. And then, of course, I need to know about whether the surface, is it a hard surface, soft surface, wet surface, dry surface, smooth or rough. These are the only things that matter. And after that, I've told you everything that you need to know. Notice I didn't say anything about the air around us because, that doesn't matter. I mean, I don't even feel the air, really. And the last time you felt the air were worried about the air in the room was when you were running up a flight of stairs and were gasping for oxygen, not because you felt the air in your face. Okay? But you do know that if you stick your hand outside the window of a moving car, you feel drag on your hand, and so it gets pulled back. So what we would think is that all these little drops that are moving out there are feeling drag because of the air there. So if we took the air away, we could get a really big splash. So this is the idea. So we want to show a truly high-class splash. And so I'm going to show you this movie again. And so this is the third time you've seen it, so get it into your mind. So this is an ordinary splash. Hits, forms the corona, and the corona breaks apart, and that's where the splash comes from. And now I'm going to do exactly the same experiment. So it's the same drop of alcohol from the same height, same size, same microscope slides. The only thing is that we put in a container that we could take some of the air out. So this is 1/3 atmospheric pressure. So this is the pressure that you would have gotten if you were at the top of Mount Everest. So you could live in here. You wouldn't be happy, but you could live there. Okay, and so now let's see the very big splash that takes place. So here it comes, big splash. So in the words of Arabi, who ordered that, right? I mean, this is the thing, is that this was not supposed to happen. And so after this, we were on the floor laughing hysterically for about a month. And before we said, well, I guess we better start doing some experiments to try and understand something about this. But, those experiments are still going on today, so this is not particularly easy nut to crack. But what I want to just show a few other movies of this. So this is now the same experiment, but now all we've done is we have a higher viscosity fluid instead of the water. So it's 10 times the viscosity of the alcohol. So it's the same thing, the same drop size, basically falling from the same height. And so we want to see whether this would splash. And so this is at atmospheric pressure, 101 kilopascal. So that's just what we're feeling now. So I let this thing go, it falls. And I stop it here because it's clearly not going to splash, right? It's just spreading out smoothly, right? Okay, so let's just finish this movie. And okay, I lied to you again. But I'm telling you these things because these are not necessarily, I mean, okay, I've seen this before, but this is what we expected when we first saw it. This is not, I mean, so I'm trying to put you in our frame of mind when we first saw this. So this thing does splash, but it splashes with a very different shape and morphology than the lower viscosity one. And you can ask, does air matter there? And so we do this thing in reduced pressure, and yep, air still matters. That is, if I take the air away, it stops splashing. So this is a very robust effect. So that what this is saying is you will not get splashing on the moon. You might get it on Mars, but not on the moon, because there's no atmosphere in that. Pardon? Everyone asks that, but you know what high pressure is? It's another word for that is called a bomb. And so we try to avoid bombs in our lab, and we would do that if there was a reason to do it, but we hadn't done that particularly. Okay, so I'm ending up. I just want to show this one last thing. So there's lots of studies you can do with this, and so one of the questions that comes into this is, where does the air matter? And so we look underneath the drop. Is the air mattering there? Is it mattering someplace else? What I want to show you is looking at what's happening above the drop. So is the air mattering as the drop is spreading above this drop? And so what I'm showing you now is a type of photography called Schlieren photography, and this is helping you see the contrast between different index of refraction of the air in different places. And so I'm going to show you just a little bit of this first. So I stop it here so you can see what I want you to look at. The drop is this big black thing. That's kind of uninteresting. That's not what I want you to see in these pictures. This black thing is a substrate. That's not what I want you to look at. What I want you to look at is, oh, you can see something about the wake of this behind. And that's what this kind of photography is helping you pull out from the, that you couldn't easily see with your eyes. Okay, and so now let's see this whole movie go. Now I'm not going to stop it, and you'll see the whole thing go. So if there's anything that maybe you can take away from this lecture is that when you go home tonight and you have a leaking faucet in your bathroom that's keeping you up at night, you can at least think that every time you hear that drop pop, something really beautiful is happening, and that shouldn't bother you so much. Okay, so this is one takeaway message. And so this is where I want to conclude, so I just want to end up with all of this. And so, I've been talking about the emergence of structure in various things, all having to do with fluids of one kind or another. And it's nature's texture. It's what really gives the texture of our world. And so I think that's something that I'm fascinated with. What gives it the flavor, the texture of what we deal with every day. And so I think it helps give appreciation to the world around us. I hope that each one of these things has been a surprise to you, because it was certainly a surprise to us when we came across this. The other thing I want to emphasize is that there have been connections throughout for all the science. So the things that we could do on this tabletop had things having to do with biology, it had to do with memory, it had to do with the quark-gluon plasma. All of these things are in different realms of physics, but we could learn something deep about them by these experiments that we do right here. And so what this is kind of showing you, these are some of the images, but nature reuses the same ideas in the different phenomena. That's the point. These things that appear on big scales, small scales, wherever, nature is using those same ideas over and over again. And we as scientists, we use the same ideas to explain them. And so this puts me in mind of this beautiful quotation from another philosopher, Albert North Whitehead, which says, "A great idea is like a phantom ocean beating upon the shores of human life in successive waves of specialization." And I think that really captures something about what we're all after and about how we see the world. And with that, I just want to say actually who did all the work in our lab. And so this is various people in our lab. So the early work that I showed you with the pattern formation, these kinds of things in the toes and fingers was done by Irmgard Fischoff-Berger, and Dr. Ramatanya, you might have seen from a couple weeks ago. All of this stuff on the drop breakup was done by these people, Michael Brenner at our home, my colleague Wendy Zhang, and then Nathan, who we introduced back there, and Laura Schmidt, who was Wendy's student. The water dome, water bell work was done by Zhang Sheng and my other colleague, Heinrich Jaeger. And then all the work on the splashing was done by all of these people. And so these are some Irmgard, but postdocs, graduate students, and undergraduates who work in my lab. And with that, I want to thank you very much for your attention.
Okay, questions? We have the mic in the back as well. I have two questions. The first one is, what would these effects, how would they change in zero gravity? And the other question is one that I think Feynman talked about and tried to figure out. I'm not sure ever did, that is, why does the spaghetti stream not break in two pieces? Do you know the answer to either of those?
Okay, so let me try the one with zero gravity, because I am not going to try Feynman's question. Just so we're clear about this, so in zero gravity, so you have to ask, well, would the drop fall at all? And so presumably you don't want you want this big drop to be held in any case, so it's actually going at some velocity. So we're using gravity to push it. Yes, so I think all of those things, so gravity, as you saw when I turned the drop around, drops out of the picture for many things because it only works on objects that are bigger than a certain scale. And the objects that we were interested in this talk were all kind of smaller than that scale. And so gravity was really not an important ingredient in the analysis of what we were doing at the end, but although it was an important tool to get the drop moving, to get the splat without the gravity having pulled down, but you could have done it by other means. So gravity was not a crucial aspect of this. Have you tried this with non-Newtonian fluid? So we have, what is a non-Newtonian fluid? Non-Newtonian fluid is been mixed with roughly 50% water, third water, 50% water, something like this. And it's beautiful. You can walk on it because it stands rapid motion. But if you can stick your finger, stick it slowly, so it has all sorts of beautiful properties. Other fluids are polymeric fluids, and so to take a silly putty, remember silly, and you watch that move, and that is fluid, is it not? It's a mixture of the various things because of the molecules that's part of this. And so there are also one non-Newtonian fluid which I did mention was the granular stuff. Sand is a non-Newtonian fluid. To the extent that it's a fluid, it's really not behaving exactly like a Newtonian fluid. And so there are other aspects that come in because of the large size of the particles. So all of these, and everything in your kitchen is non-Newtonian fluid, basically. Anything that the chemical companies have got their hands on is non-Newtonian. Can probably guarantee that. And so there are things, so we haven't done those non-Newtonian fluids, but other groups have. So they've looked at things having to do with the drop breaking apart. And there are differences depending on what the constitutive laws are for that particular fluid. There are different kinds of things. And so our emphasis here was to take the simplest thing and see if we could understand it. That was where we went. But then other people have gone and done more on that in these different ways.
Still does the necking?
So some things still do a necking. So if you put particles in, this thing comes in and necks. So a granular, so a very dense suspension of grains in the liquid, then you can, where the grains then start poking out as the thing is falling, then you get kind of fracture in some of those areas where the thing breaks apart. So, but you do get, until you get down to that particle size, you do get this kind of necking behavior. And there are various laws that people have been able to measure for that. I mean, there are different laws than what we got in this case, but they are, but you can analyze it. Now that you know something about how to analyze it, this gives you a way of doing it. Questions? So we'll do something like that.
In the Schlieren photography that you were showing, I was having trouble parsing visually the last part with the curling going on. Was I seeing half of it, and it's really like that all the way around?
Yes. So I am really surprised at how nice that turns out. I mean, so it's doing this in, it's a donut, right? And so you're seeing all of it. But when you see it here, you don't really see anything of the structure. And so it's only at the edges that you see the structure. It wasn't that we try to focus on just those edges. We were still focusing on the whole thing, but that's the part that comes through. So that is, you're surprised, and I'm surprised too. How nice that turns out. But these people were very good at it.
How much of this is really surprising to hear myself about necking
Yes, when we worked with Michael on this, he was a student, and the computer simulation that we did in those days was not very good at having two different viscosities. So that was one thing. So that's something that's still a problem even now, to really be able to get big viscosity contrast in these so that's one thing. The second thing is that in I showed one of these, so let's see if I can get back to this one, I told you it long thing forms in half. Okay, that you could have gotten from the Navier-Stokes equations. Okay? But I said that the next step comes down a little later, gets thinner. That's not the Navier-Stokes equation. That's noise. inherently always is there because it's so sensitive on the atomic scale that even when you're 1 micron neck size, so you can still see it, if one atom was out of place, that would have been enough noise to trigger the next thing over and over again. Well, it was a deep mystery at the time. But as we did not, before this, we did not know how to think about this appearance. We did not know that the right way to think about this is, yes, so we learned something. And the other thing is that what we were told at the beginning was that all of these things should be universal. And then I showed you the air bubble, and the air bubble is not universal. And so then you ask, okay, so what's happening there? And now I'll tell you kind of why that shouldn't have been universal. And everything in retrospect is obvious, Jim, but before, I mean, you know, theorists are great at predicting things after the fact. And so, you know, that was...
when we get it right beforehand, you never shut it up. Okay.
Well, that isn't quite true. You're my best friend forever, and, you know, we'll talk about this later. Okay.
Thank you. Let me just remind everybody we have cookies, drinks, etc. Before here. Please don't leave it all in the post office.
This about stars. I was playing these two instruments. And so what you are hearing were sound waves that I created by blowing a big flute and a smaller flute. Okay? And the bigger flute had the lower tone, and the smaller flute had the higher tone. I want you to remember that throughout the talk, because that's part of the story I want to tell you. For me, stars and star quakes, stars are just instruments, musical instruments, and so that's why I always like the analogy with music that you know of. And I see this beautiful piano here. I didn't know it would be here, but I can't play it anyway, so I couldn't take that challenge. So let me start off by moving to stars, and stars are shining. Yeah? They are shining because they happen to be able to do nuclear fusion. They are nuclear reactors. We humans cannot do that very safely here on Earth to create energy, but stars are really stars in that. Yeah? And so they shine. In contrast to planets, I want to set that straight because this talk is about both stars and about planets. We do see the planets of our solar system in the night sky. That's because they reflect the solar light. So planets are not able to create radiation in the same way as stars do. That's because inside the stars, the temperature and the density of the gas, because stars are just gaseous spheres, is so high that they are able to do nuclear fusion, nuclear reaction. So this is a complex process that creates radiation, and that's how stars shine. So because planets cannot do that, they can just reflect the light of their host star, so to speak. They are much fainter in brightness. And so you have to imagine that if we would be somewhere else in another galaxy, and we would be looking at the sun, we would not be able to see very easily the planets orbiting around the sun, because the solar light is overwhelming. And nevertheless, we want to go and search for planets around other stars. But that's going to be the second part of my talk. So stars are nuclear reactors, and that's you should be grateful to the stars, and you should particularly be grateful to my pet stars. These are stars that are massive, as we say. So they contain more in about, 5 billion years from now, because the sun is halfway through the star. Now that's not such a pleasant period for us here, because the sun will swell up, and the radius will become huge. And so, at that moment, we are hitting a real global warming phase. Yeah? You don't have to be too here because I have a microphone. I went out the room so that you didn't see me. But still, you heard sound